All right, there we go. We are now recording. Hello, everyone, and welcome to the Advanced Artificial Intelligence Workshop. Thank you for joining us. Today is going to be myself, Luke Parkhurst, and Damian Musk, who will be with us, and we'll be presenting to you all the different types of models, warning algorithms, and some of the mathematics that come behind artificial intelligence and how an artificial intelligence construct is actually made.
Now let's begin by defining what a neural network is. At the It might at first seem like an abstract concept, but really it's exactly what it sounds like. So first, artificial intelligence is an approach to machines using human-like thinking. In other words, we model our human intelligence artificially with computers, hence the name, modeled after how our brains and human cognition actually function. That's where the term neuron comes from. A brain cell, we'll be talking about that in more detail later. So it takes in and transforms data that may be quantitative, sensory, imagery, sound, etic, to adapt to its environment and perform smartly, just as we do. And neurons are in to help activate and process data fed through the algorithm through activation functions, which John went over in the beginner's workshop. So these neurons are nodes that help train the algorithm to create the right process and minimize loss. Akin to how our brains consist of billions of neurons that communicate with each other. So we use weights and biases to help activate neurons to train the algorithm, as John discussed.
All right. So apologies. The types of machine learning that we'll be going over today, the most common ones anyways, are four primary, is going to be supervised, unsupervised, reinforcement learning, semi-supervised learning. There are other forms of classification concerns on how exactly neurons interact to form network, as you'll soon see. Now, while these are the four primary types, there have been other suggested models for different types of learning.
So beginning with supervised learning, these types of models learn functions that map inputs to outputs based on how many input-output examples are given, inferring the desired behavior from labeled training data consisting of training examples. So it's a lot like the teachable machines example. So basically we just give it data, we give images labeled cat and dog that we labeled ourselves, and then by analyzing each one, it learns how to classify them. What exactly in this image makes it a dog, and what exactly makes this image a cat, and how can I use that information for data outside the training set? So it's like teaching someone the difference between dogs and cats, just like a small child, by showing many examples of them, and then teaching them to extrapolate. For example, um, in like a first grade health class where we teach children that these things are fruits and these things are vegetables. From there, can you extrapolate what other things are fruits and what other things are vegetables? The examples used are pairs consisting of an input object, which is usually a vector that we can perform dot products with, and the desired output is known as the supervisory signal. And finally, the inductive or learning bias is the assumption used by the ML model to evaluate inputs not included in the examples. So for example, there was the minimum description length, which is a little like an application of Occam's razor, which states that the best answer is usually the simplest one, informing a hypothesis and aiming to minimize the number of words needed to describe it. So a key supervised algorithm is called KNN, or K nearest neighbors, wherein we load the data and set K to the desired number of neighbors. Actually. Sorry. Sorry, we didn't kind of cover this later, but this is an example algorithm that relies on the assumption, the inductive bias, that neurons that fire together wire together. So basically that in feature space, the space of all of the features that are being looked for, the ones that are most similar are going to be closest apart. So we take the distance to each neighbor and then try to minimize that. So in the algorithm, in this procedure, we load the data to find the desired number of neighbors, and for each training example, we calculate the distance and add to the distance and basically make a dictionary with the distance and the index of the example. Then we sort the ordered collection and indices from smallest to largest by distance. We pick out the first k entries and then get the labels of what we're predicting of the selected entries. And then finally, if the problem is on regression, we return the mean to add to get the approximate relationship between two analyzed variables that are being modeled in feature space. But if it's in classification, we return the mode. The most common one is probably the category of the thing that the system is examining. Now, next, unsupervised learning is a little more complicated than supervised learning, as it has minimum human supervision, and there is thus no teacher to tell it what is right and wrong. Instead, such models look for previously undetected patterns in an unlabeled dataset and model probability densities over inputs. So they use probability to learn what to do. So it's a little bit like trying to when you've just learned a language and you're trying to read a book in that language. So you might not recognize what a few words mean in a sentence, but you get the gist of what it's supposed to mean and you know most of the words in the sentence. So therefore, you consider what is in all probability the right answer and you assume that that's going to be the right answer. And so basically the statistical procedures used in this type of unsupervised learning are just like a more complicated version of that. So we will discuss the exact details of unsupervised algorithms a little later, but one of the main ways to recognize these patterns is clustering, which groups sets of objects in such a way as to make similar tasks closer in proximity. So it's like a more general type of k-nearest neighbors algorithm that's applicable when the training data isn't necessarily labeled. So it has many real-world applications. We'll talk about more applications later, but these include customer segmentation.
Oh, I think we might have lost him. Damian, are you still with us?
You're muted, looks like.
All right.
He's probably taking care of some background.
Yeah. All right. So, Luke, you want to
I'll go ahead. I'll pick up from here, yes. So the unsupervised learning examples, we have a couple of them, and the unsupervised learning examples has real-world applications. This includes customer segmentation or understanding the different customer groups around which to build marketing or other business strategies. Recognizing patterns and appealing marketing has also yielded some interesting insights in psychology. You'll actually note that a lot of this gets used in forecasting and prediction later on. In genetics, such clustering DNA patterns to analyze evolutionary biology, such as unsupervised models, are one of the centerpieces of computational biology. This can also be seen in some of it where they're actually doing cancer research for dendrograms. And the recommender systems, which involve grouping together users with similar viewing patterns in order to recommend similar content. Most social media websites employ unsupervised learning. This can also be commonly seen in sites such as Amazon, where there's suggested purchases depending on your age group or the group that you normally buy in, or the shows you watch on, say, Netflix, Hulu, or whatever show streaming service you prefer to use. It's also available in anomaly detection, including fraud detection or detecting defective mechanical parts, which is predictive maintenance. That's where some of the predictions and forecasting comes into play. Now, working into semi-supervised learning. Semi-supervised learning is a learning model that's trained with the usage of only some labels. Labeling all your data takes a large amount of time and a large amount of space. By only labeling a few data sets, though, the model learns how to classify similar data sets. Pretty much, it's similar to supervised learning in the sense that it's extrapolating how similar these groups are and then categorizes them correctly. This is typically used with documents or any type of categorization or classification. With the pseudo labels given to the unlabeled sets after labeling the real sets, the labels between the two sets are linked and so is the data. A process is repeated multiple times to improve the learning model's accuracy. So over time, if you have multiple articles, some of them might be opinion articles, some of them are research, some of them are just newspaper clippings. Because a computer can read thousands of words in a minute compared to the human brain, you teach it how to classify it using different types of fonts, setups, anything like that from pretty much how the paper should look. If you say, all right, a research paper has these sections, uses this font, and uses these type of citations, if it reads a paper and it has none of that, then it's not going to label it a research paper. Now, why semi-supervised learning though? It helps the model builders obviously to use and label only a small portion of the training set. As I said, labeling takes a long time because that means humans have to read each paper, and we don't want them reading each paper. That's what the whole machine learning is for, to read the papers for us. And the amount of space that's required actually writing down vectors, classifying what it is, when we can have it all simply categorized together with a machine putting it in its own groups. It also allows the models to be trained with higher accuracy while avoiding labeling all our data sets. Some classic examples. Sorry?
Could I ask, so, once you do the clustering, now sure, you're not labeling the data beforehand, but you would label the clusters afterward, correct?
Yes, you would have some of them together. You would create the clusters and some of the labels at the very beginning. So let's say, for example, you have 9 different articles. Now, we'll say 2 of them are opinion pieces, 4 of them are going to be newspaper clippings, and another 3 are research articles. You'll take one of each group and classify one of each. You'll say this one's an opinion, this one's a newspaper, this one's a research. From there, you're going to simply tell it, all right, go through the other 6 documents and put them in the classified clusters we've already created. So now, instead of having a human read the other 6 documents, the machine reads them, and it'll find the last opinion paper, put it in there. It'll find the other 3 newspaper articles and put it with the newspaper article, and then the other 2 research papers and with the research paper. This saves a lot of time because instead of having to read all 9 and classifying them, they've only read 3 and classified them, and then asked the machine learning algorithm to classify the rest.
That's pretty smart.
Exactly, and it saves a lot of time since a computer can easily go over thousands of pages much quicker than a human can. So that would be our document classification, which is our first example. And the labeling and classifying, which technically falls in document classification, but there's some arguments with document classification on exactly what the extent is, whether or not a document classification can fall under a larger category, such as trademarks, copyrights, etc. Now we also have, oh yes, sorry, go on.
So like, could you use, you would use like semi-supervised learning. Let's say you had like a lot of tweets and you wanted to like go through the tweets and you wanted to like label them as like, I'm going to say specifically because something I'm interested in, but like you're trying to find like anti-Semitism on Twitter. So you like go through and let's say you have like 1 million tweets you want to go through, but like you label maybe like 2,000 of them sort of, and then you kind of let it do the rest sort of.
Yes, in a sense. There are other forms that might be better suited, but if you want to do semi-supervised, let's say you had a training set of 100 tweets and you're attempting to stop anti-Semitism, you would say out of the training set, you would find 10 of those tweets which are anti-Semitism, and you would tell the algorithm, these are anti-Semitism because of these words or because of this setup. And from there, tell it to go through the other 90 tweets and hope that it captures most of them. Now, these algorithms aren't 100% foolproof. It might miss a few, it might accidentally classify some of them when it shouldn't have. But for the most part, if it's properly trained, the algorithm should pick up, I would say, about 80 to 90% of it. So you'll find that as it goes through the other 90 tweets, it will pick out the majority of them and pull them back. So therefore, you'll have an increased training set. Now, this grows even more useful because this is where you start telling it to retrain itself. If it correctly pulls them out, you say, all right, all of these are correct. And any of them that are incorrect, you take those and remove it from the new training set and say, here's your new training set of these 19 tweets that are now anti-Semitism. If anything looks like these, you pull it out. And you continue training it in such a similar manner. Does that answer your question?
Yeah, pretty much. Thanks.
Yeah, not a problem. So reinforcement learning is our fourth type we'll be going over. And it's a process that's like an unlabeled puzzle. It's like giving someone a Rubik's Cube and asking them to solve it. Now, you can set points on the individual answers to the puzzle and tell it to solve. For example, we might tell someone, we want you to solve this as fast as you can, or we want you to solve it in as few moves as possible. Those are two different ways to do it, and we're going to give you the most points if you do it either the fewest way possible, or we'll tell them you get the most points if you can solve it as quickly as possible. From this, the model then does the puzzle multiple times to find the maximum points rewarded. So if we tell it we want to do it as fast as possible, and we give it a Rubik's Cube, we'll find the algorithm will do the Rubik's Cube as fast as it can multiple times in a row, each time doing better than the last. And if it can finally reach a 1 point and find that's the most points it can get, it will then choose that as the optimal answer. Otherwise, if we had asked it to instead give us something in the fewest number of turns and hand it a Rubik's Cube, we'll find that it'll do every possible solution it can and then return back what's the fewest number of turns or rotations it needs to do to finish the puzzle. So puzzles in our broad term is a task. We want it to complete a task. And it includes telling the model how to complete the task with different parameters. Our parameters being how fast you want it or how maybe in the fewest moves. And a similar task may have different goals, which has the model to relearn for the goal requested. So the overall task with a Rubik's Cube is solve the cube. But we have different goals. How fast do we want to solve it, or how few turns do we want to solve it? Some pretty good life applications is automated vehicles. Automated vehicles, which as we know are starting to become huge, especially as Tesla has shown interest in them, is that the general task is to get to your destination. But how should we get to our destination? Do we tell the automated system to go as fast as possible, or do we tell it to go in a straight line? Hopefully not a straight line, because I doubt there's a road that's straight line unless you find a tree. So in this case, we have to tell the automated vehicle the most efficient road, our fastest time there, or prioritizing the safest way to get there. Maybe it'll do some type of lookup on roads for Google Maps and say, all right, this road's reported having multiple accidents and is being dangerous. So we'll avoid this road and reroute through another road. And the points are awarded to this system for the goal that's being chased. Another rather popular one, and one that I personally love, is called the knapsack problem. Granted, the knapsack problem isn't technically an applicable thing in life, but the actual idea of it is extremely applicable. It's a popular dynamic programming problem, and the task is to put various items of different weights into a knapsack. The problem can have its goal change for the points. So when you have a knapsack and different items, we're going to say we're Indiana Jones. You're inside a pyramid, your knapsack can only carry so many pounds, but there's a lot of treasure around, and each treasure has different value. You'll find that an old arrowhead's not going to be worth as much as a golden idol, but the golden idol is going to weigh 10 times as much as that arrowhead. So what's the most efficient way to put stuff in the knapsack? And that's going to depend on your goal. Your task is to fill the knapsack. Your goal is going to change depending on what you want. Maybe you want the highest value. So you'll take the weight of all the items there, and you'll keep doing different combinations until you can find the combination that gives you the highest value that your knapsack can technically hold. Otherwise, our goal might be the most items. So from there, you'll start with the items with the lowest weight and keep putting them in until you can no longer put them in, or find different combinations which allow you to hold more. These are just simple examples on how you can change the goal for it to ask and get rewarded points. Now, once you've created a model, something you have to understand with any learning model is there's some stuff like backpropagation. Backpropagation is, I'm going to say simple, but it's not quite simple in reality, process of tweaking the weights of each node by traveling backward through all the nodes in the network. For the most part, it's more of finding out where the small errors are. All right, was this weight correct? Did we technically get the end output we were expecting here? Did we pretty much see what we were expecting from the machine? If, for example, we did any type of classification and we told the semi-learning model that we're going to give it a bunch of pictures of cats and dogs, and we want it to construct us a picture of a cat and it returns a dog, then something went wrong. We do backpropagation to find where it made these slight problems. And then we tweak the weights as needed until eventually it gives us the answer that we're looking for. Does someone have a question? No? All right. Damian, is Damian back on board?
I was just talking to Damian, so he has some technical difficulties. So he's struggling a little bit to get back on. So I'll try to figure out how to get him back on here.
All right, I'll continue going. I just didn't want to steal the limelight of the show. All right, so the next topic we're going to cover is gradient descent. This is part of backpropagation as well. Gradient descent is a process of minimizing the loss outputted by the neural network's output. This is an iterative process, and for the most part, it's correcting what the actual output errors are and just iteratively going backwards and finding the right process until you finally get the more correct answer. So if, for example, before backpropagation, you expect a classification algorithm to hand you a cat and hand you a dog, that's severely off. So then we go backwards and we say, hey, we need to fix the gradient descent. We're going to do this algorithm now and tweak these weights. So then the new output that gets put out is something that's a dog, but with cat ears. Well, we're getting closer, but we're not quite there. So we go back to the gradient descent, we go back to the backpropagation, we go back through the weights and through the process of gradient descent, we refix it. So now when we go back, it then says, all right, here's a dog with cat ears and whiskers. It's still not quite there, but we're closer. And this process continues happening until over time, it gives us what we're expecting for our output, which is the image of a cat. And it could be an iterative process that's done in a single run. It could be an iterative process that almost never ends. Hopefully not, because then it becomes a Turing machine. Now, there's a few type of neural networks that we're going to go over. The thing with neural networks is these aren't the only type. There are dozens of types of neural networks, and almost every month they're coming out with a new suggested neural network. Neural networks, though, all have different possibilities and different uses. One neural network might work better with different types of learning models. Another neural network might work better on a different problem. So no neural network is specifically going to work with all other problems or learning models. You'll find that what you might expect to work works only possibly or partially of what you expected, and another model that you didn't think of or someone has suggested might work much better. The types of neural networks we'll be going over today, though, these are more of the common ones, are feed-forward neural networks, the convolution neural network, recurrent neural network, and the auto-associative neural network. So our feed-forward neural network is the simplest of neural networks, in opinion, in fact, that there's typically no extra middle nodes for it to feed through. Most of these are simply an input to output. There might be hidden nodes in the middle for hidden weights, but for the most part, a lot of them are just simply in and out. It was first created for AI ML, and it was the first one suggested, and it works by feeding all the input for nodes going forward only. Backpropagation is a little tricky on feed forward because backpropagation doesn't always exist in some of these, since the whole point is you're only moving forward. Backpropagation does exist in the sense that we only have it going backwards for it, as we suggested on here, but typically it's to some degree, especially since all you have is input and output neurons. There is no loops for these, and the only nodes include our hidden groups that we might have given for our output, which is typically any weights we need to go through, and it's our mostly used supervised learning model. It's easier to program versus its counterpart, which is recurrent, and the easiest example of it is going to be a perceptron. So our convolution neural network, weird, I think we're missing a slide there. Our slide's coming later. Our convolution neural network, used mostly for image recognition. This is a little interesting because this is where the famous question is coming in. How do you classify something? Is this a cat, a dog? Is this a bike? Now, this is where the question of the captchas come in. I don't know if anyone here has ever done anything with the captchas as, are you a robot or are you human? A lot of the captchas typically are asking for something along the lines of imagery in which it wants to affirm that only you can read. But with a convolution neural network combined with some type of semi-learning model for classification, you can technically make an AI that would actually beat or go through those. With the convolution neural network, it's used mostly for image recognition and utilizes a convolution layers, also known as filter. It creates a window of a size subsection of the image and feeds the entire image through it. So it takes a single portion of it and actually feeds the whole image through it, creating this window saying, is there any similarities in this? By utilizing the color lighting recognition, white to black being 0 to 255, 0 is white and 255 should be black. Once I got this reversed, but that should be it. And preserve the original image dimensions. A buffer of zeros is typically added. It's suggested it can be, but you'll find most of actual neural networks add a buffer of zeros around the overarching image as it goes through. And here, as you can see around our boat, there's a dark blue line on the actual example given, and the dark blue line would technically be our buffer of zeros, so that way we'd hold on to the original image. It then compares the found image to the given labeled inputs, cat, dog, bird, fish, etc. So in this case, we would actually feed it, if we wanted to learn boats here, for example, we're going to feed it this small subsection of boat, as you can see a small square taken out of it, and gets sent towards the actual pooling. It then goes through the whole image, finding any similar sections of that coloration, that light, that anything such as that, and rebuilds the image going smaller. Once it finally rebuilds the image compared to a database, it says, all right, in this database, we'll find that we have numbers that are similar to this. So if we feed it a boat that's also white and blue, it's going to find through that boat going through multiple numbers that are grouped together of the same coloration. I believe blue is going to be a coloration of red and, nope, it should actually just be blue. Yep, RGB. So it's just going to be blue. You'll just have straight blue being set up to 150 to 255 for a darker shade of blue towards it. And this little line here in the boat, what it's going to do is it will compare it to other images in the database and say, hey, we have other boats that are just like this. So this must be or similar to a boat. It will then feed back going through the different parts of the boat and feed it straight through the actual window going forward. And as it finds more sections that are similar to its training data sets that are a boat, it will hopefully come out to our final image and say, this is most likely a boat. Now, the recurrent neural network, which is the brother to the feed-forward neural network, is a connection between nodes that form a directed graph. It allows it to respond dynamically of time, and it consists of a single layer where every unit is interconnected and all units act as input and output. It's enabling the network to store patterns rather than merely pair them. This, an RNN, takes up a bit more space than the feed-forward network, and while it has more uses, one of the problems with it that has been considered is the disk space that would be required to hold onto it, because you're holding onto a larger training set. It's used for variable length sequences as both input and output instead of most other neural networks, and examples of these are obviously going to be shown below. So doing a one-to-one from one to many, we'll find that we use the same items, but we actually feed them through the same filters. This helps pretty much speed up the actual length of it while making sure that we're not going too far and creating too many nodes, as our input is also our output. are auto-associative neural networks. An auto-associative neural network, ANN, is a fairly recent development. These have actually only come back, and I want to say probably the last, well, it's 21, so 5-6 years now. An auto-associative neural network is a fairly recent one. ANNs are feed-forward networks, connections between nodes that do not form a cycle, unlike RNNs, trained to approximate the mapping between input and output using backpropagation or similar learning features. The approximation gives a bottleneck layer and an intermediate layer that is dimensionally simpler than the input layer. This type of bottlenecking allows the network to engage in titular auto-association, wherein something with only a tiny sample of itself can be extrapolated and completed. So, take for example, we have the finishing to be or not to be, that is, and which would practically tell it that it would have to finish that line. As a result, it's particularly useful for anomaly detection. And up here we have our small example of it, where we feed our error input, send it for the mapping, bottleneck, demapping, and output. For the most part, a lot of this comes in through anomaly detection and some type of form of forecasting or prediction. We want it to guess what it's going to happen next and if there's anything wrong with what's currently happening.
I'm not quite sure what the purpose of the bottleneck is.
So, bottleneck. The whole point of bottleneck, trying to find different words to put it in now, are a little better than what I'm saying. I believe the whole point of a bottleneck here is it serves as a slower filter. It wants it filter in its own, it pretty much wants it to turn back and look at itself. So as it's finishing, we want it to actually take a second. I guess if I want to put it in more general layman terms, we want it to sit down and think of what it actually is or what it's doing. So an auto-association example, another good example, auto-association example is, I would say, having something look back on what it is as an image. If we went back with some type of imagery example, we'd ask for it to look back on what it actually is. Pretty much from what I'm getting as a decent example here would be a memory of knowing exactly what you're looking at. Let's say, for example, I'm going to give you a picture of the top of a Coke bottle. Now, I'm not going to show you the words of what the Coca-Cola are, but it's going to be the old Coke bottle that you've actually seen. And I'm going to ask you from your own memory, going through the bottleneck filter, what do you think this is?
Well, so you showed me
A Coke bottle. We're going to show you a Coke bottle. We're not going to show you the label of the Coke bottle, like the company's name, but we're going to show you the old glass time Coke bottles where it looks like a Coke bottle. And we're going to ask you, what is it?
Well, I wouldn't be able to tell you it's a Coke bottle because it wasn't labeled.
In your memory, it would be labeled. That's for the whole auto association. Is that would give you a test? Sorry.
Oh, so you've shown me you've shown me the whole bottle, and then you show me only part of the bottle.
Yes.
Oh yeah, I see what you're saying then. So it's like short-term memory.
Yes, my apologies there. That was poorly explained. But yes, that's pretty much it, is that we do the mapping, then we show you a piece of it and we say, all right, what is this? And it's pretty much a reinforcement. You sit there and say, all right, if this is the bottle and this is our bottle neck, no pun intended, if this is our bottleneck, then what is this image? And as the auto association machine, it should hopefully, through demapping, say, oh, that's the top of a Coke bottle.
I see. Yeah, that makes sense.
It's more focused on memory. I'll admit this is not one of the neural networks I'm typically well-versed with working with. But as I said, this is a relatively new one that's only popped up in recent years, especially with the question of actually psychology and machine memory in mind. So one of the things I do want to go over, if we don't mind going back here, is we did have a few other examples of mostly what each one was. Now, for the perceptron, I'm a little unsure where our slides disappeared to. Don't know if it got saved correctly. But a good single layer perceptron would pretty much be nothing more than the input and the output, in which we did have one that shows it would send in inputs for any type of vector that you wanted it to read, and simply would look at it and associate it with what you need and then put it in our output. Perhaps not as descriptive as I wanted, but as I said, we seem to be missing a few slides. Convolution, we did have another slide that showed a bit more into actually how it broke it down. As you can see here, this example shows a nice quick breakdown of it, but it's not exactly what I was hoping for, as there's a bigger breakdown where it actually shows through and it shows the numbers. So for example, if we had a picture of the number 1, you'll find that as it goes through, we'll say it has a black background and the number 1 is in pure white on it. It will go through and say, all right, the black background is all numbers 255. And then as it takes a box, a square really, of if the picture is a, say, 6 by 6 for an overall 36 pixels, we're going to give it a box of 2 by 2 and tell it to go over every part of the actual picture. And when it recognizes, when it hits part of the 1, it'll say, all right, this one is white, so it's going to be 0. And it starts taking groupings of zeros together and forms in its own memory a pseudo image with the actual numbers of colors. That's better how to explain that it's actually doing it. So in this case, as it goes through a boat, it's going to end up going through each section. Say this boat was a 6 by 6 on pixels, and the little square here was a 2 by 2. As it goes over the boat, it's going to find similar color groupings. Since this is all white, it would say this is a group of white. And it would continue reading through this, and then it would say blue, this is a group of blue at color 90, and then at color 150. And it will continue going through the image of it and separate between water and boat. Then when it feeds onto another image that you gave it, in its memory, it's going to have perfectly saved what the idea of a boat looks like. If it finds another boat that's extremely similar to it, we'll say we're going to have a boat here without the captain's quarters. But by going through the guardrails, the coloration of the trim, and the white bottom itself, it'll say, hey, there's a large chance this is a boat by following the similar patterns in coloration. So that's what convolution is. And I do apologize. I'm a little unsure where those slides went, but I was hoping to break down a little better what each one of these did. Now, our recurrent one, our good recurrent example is pretty much, lack of a better term, a single layer in which we had to practically go in and out almost immediately. See if I can't find our example. Nope, I do not know where. For lack of better terms, it's a single layer in which it simply enters and then exits almost immediately, and it practically utilizes only a single set of neurons, unless there's any hidden walls that it has to go through. So from there, we'll go ahead and go on to our important algorithms, a bit more favoritive here. And our first major algorithm we're going to go on about is dynamic programming. Dynamic programming, I'm partial to. It's a lovely system, and it's a methodology, geology, not only used in machine learning, but in several other prospects. The whole thing about dynamic programming is it breaks larger problems into smaller, easier subproblems, and it assumes all input parameters and rewards are correct. Now, there's 3 types of machine learning dynamic programming algorithms. We have our value iteration, policy iteration, and policy search. This is a good example here where our paradigm is it's a divide and conquer that's broken up into overlapping subproblems and optimal substructure, plus the methodology of memoization and tabulation. This allows it to help actually reduce covering the same problem over and over again. When you do a divide and conquer method, for example, we're going to say something like a binary tree. If you have it do a recursive algorithm, you're going to find that it's going to end up spitting out some of the equations again and again and again, and they're the same answer. But instead of having it redo the same equation 3 times, you have it do it, and you have it right in a table. Hey, here's the answer for this equation. Then when it does the equation again, it says, hey, before I spend time solving this equation, is it in the table? Because if it's in the table, I already know the answer. I don't need to spend time solving it. And dynamic programming is a pretty popular approach. Knapsack problems actually the paradigm of what a dynamic programming is. Now, in a machine learning aspect, we have three major ones, and it simply comes down to policies when it comes to machine learning. Policies, for example, is set for the process or the actual, I would say, rules you set for it, in which you want it to improve itself when it learns. In value iteration, it's a simple backup operation combining policy improvement and truncated policy evaluation steps. With each sweep, it institutes one of each of these. It will go back and say, all right, so we got our output, but was it optimal? Can we improve it? And how was the evaluation? Did we get the output we exactly wanted? If not, it continues tweaking it and it'll continue changing. Does someone have a question? No? All right. So then we now.
No, but it appears Damian just joined, so hopefully he'll be able to work out his technical issues in a reasonable amount of time. But yeah, I just wanted to let you know.
All right, that's not a problem. Next, we're going to go over to policy iteration. It's a process involved using policy W and then improve it with a function of V of W for W prime. Now, W, these are just variables. We don't need to go too far into it. When we say policy W, it can be any letter, anything whatsoever. We're saying it's a policy, and we're going to run it through any function. This function we call V. We say it's V of W because we're specifically running the policy through the function to receive our optimal policy, which is W prime. We continue repeating this process again, this time taking W prime and sending it through function V to receive our new policy that's optimal, which is W prime prime, and so on to continue improving our optimal policy. This is just a policy iteration in which it continues doing the policy improvement and the policy evaluation over an iterative process until you more or less deem it's fine enough. You would have to set a parameter to say, all right, when you've reached such and such evaluation, or you've reached a 90% goal maintenance for output, you'll tell it to stop its iteration. Our final one for dynamic programming is policy search. This is a process where a map of policies is given, and it uses the algorithm focused on finding the most optimal policy for a problem. So you give it a bunch of rules, and you say, all right, these rules go together, these rules go together, and these rules go together. And then you create a map with all three sets on it. Then you randomly assign any set of rules to it. We'll say we'll set second set of rules to it. And the second set maps back to the other two and say, run it with this one. And if it doesn't think it's optimal, it'll check one of the other sets of rules and says, all right, we'll go to set rule 3. And if the third set works better, we want to stick with that. Otherwise, if we go to the first set and that works better, we want to stick with that. If it turns out neither set actually runs more optimal, then we found the optimal set, which is rule set 2. Damian, if you're on board.
Yes, I can talk about this. So, moving on to random trees. So these are an ensemble learning method for many ML tasks, in that they tie together multiple techniques, some of which being the things we've already talked about, and can solve problems other than classification and regression, since, of course, machine learning goes far beyond that. So it creates decision trees consisting of possible choices and consequences to go from observations about items, so the tree branches, to conclusions about the target value. So in classification problems, the target variable will take on a discrete set of values, such as cat, dog, or other. In regression, the target is continuous, since you're trying to find a multivariate relationship. So with a multitude, a large number of decision trees, the model will output the class that is the mode of the classes. So basically, again, turning the probability, the thing that the system most likely thinks the output is by taking the most common value, or the mean prediction of individual trees, which is analogous for a continuous data set. And randomizing trees used can help mitigate overfitting to the training set, in that the training set won't exhibit some particular pattern that will occur, that doesn't occur quite as frequently in real world data. So they're commonly used in operations research, which is and decision analysis, which allows us to employ a plethora of various statistical techniques. And because of that, it also has a lot of applications in modern psychological science.
So,
Now,
apologies. Going on to linear regression. Linear regression is one of the ones I've also used quite frequently, and linear regression works with predictive modeling and a lot of different type of forecasting. One of the biggest problems of machine learning and predictive modeling as a whole is minimizing the level of error or noise present. Linear regression is a popular supervised method of doing so. Being a supervised method, it makes it a rather preferable method as it's very easy to implement. In our simplest regression problem, the model was looking for the equation y equals b0 plus b1x. And there are 4 ways of doing this. The first is our simple linear regression uses standard basic statistical methods and doesn't need ML. It's not very sophisticated. And our second one, which gets a bit more into it for ML, is our ordinary least squares. It's useful in the case of more than one present, minimizes the sum of the squared residuals. Difference between the point on regression line and data. Gradient descent, as we have discussed, the gradient descent is very useful for one or more inputs and works by starting with random values, calculating the sum of squared errors, and using a learning rate as a scale factor, and continually updates coefficients in direction towards minimizing errors. This is given by our gradient vector. Regularization is our 4th method for doing this, and it seeks to minimize squared error but also reduce complexity of the model. Our lasso regression, which minimizes absolute sum, called also L1 regulation or regularization, and ridge regression, which minimize squared absolute sum, called L2 regularization. Linear regression is one most commonly used, but as you can see, with how simple it can be, it's not always used for machine learning. You don't exactly need it. For the most part, it's simply using statistical means. With different methods, you can bring ML into it, but it's one of the more preferred ones as it's the simplest.
So we can now return to another discussion. Sorry, there was a lot of background noise, but we can now return to our discussion of k-nearest neighbors in more detail. So again, it's the most common type of supervised learning, and it can be applied to problems involving classification and regression. It gives our machine learning model an input of the k closest training examples out of all possible features. This is a domain we call the feature space, under the assumption, so inductive bias, that similar data points exist close to each other. In other words, birds of a feather flock together, or as the neuroscientist David Hebb would say, neurons that fire together, wire together, and in fact, that philosophy is what fuels Hebbian learning. So for continuous variables, we generally take the Euclidean distance, i.e. the Pythagorean formula. And for discrete variables, so for example, in the sentiment analysis of text, we use a different type of metric known as the overlap metric or Hamming distance, which is going to be the number of positions at which the corresponding symbols are different, or in other words, the minimum number of substitutions required to change one string into the other. So it's just like another way of measuring distance, but we're analyzing a different type of thing.
One of the last ones we'll be going over is our learning vector quantization, or LVQ. It's a space-oriented approach and very different from other methods. The whole point of LVQ in some methods versus KNN or random tree is that it's attempting to save space by only actually choosing what training sets or what training data is the most optimal for it. Unlike most algorithms, it allows users to choose what training data to keep. So if we have a training set and we want it to learn how to use any type of forecasting to predict, for example, we want it to predict what's the best day we're going to have people go eat ice cream. So we're going to feed it types of data for all the information, all types of weather, everything. But we're going to need to find the most optimal day. So it's going to have data saying 32 degrees all the way from data ranging upwards to 100 degrees Fahrenheit. And then we're going to give it another variable, for example. We'll say, all right, this is how many people bought ice cream and compared to temperature. So the training data will say, all right, at 32 degrees Fahrenheit, no one bought ice cream because it's too cold. But at 50 degrees Fahrenheit, 2 people bought ice cream. And it will find that as it continues along going upwards, it will say get to 80 degrees Fahrenheit, 100 people bought ice cream. But then when it gets up to 100 degrees Fahrenheit, we'll find that only 70 people bought ice cream because now it's too hot to go outside. So from there, it starts picking and choosing the data as new data comes in. If another day comes in and the day is listed at 40 degrees Fahrenheit, and it already shows a lower number than the actual higher averages, the machine will automatically take that data and throw it away because it's not useful and it's not reaching it to find when the maximum number of ice cream sales happen. But if a training data came in and said, hey, it's 85 degrees and there was 120 ice cream sales, it's going to keep that data and replace an older, unused, unoptimized data. So if our first piece of data is 32 degrees Fahrenheit with 0 sales, it might take that data, throw it out, and instead replace it with the new data for 85 degrees Fahrenheit with 110 sales. This way, it says, hey, around this range is when you'll find the more customers, and it takes out the old data. It allows it to improve and optimize the exact training data that you want the algorithm to hold on to. In this case, what temperatures we can expect for a forecast model for ice cream sales. As I stated, or as I've been trying to show, it's widely used in forecasting and particularly my favorite for predictive algorithms, especially when it comes to sales, predictive behaviors, customer turnouts, or market behavior. With training sets that pertain closer to what is required, the forecast algorithms can be optimized, and it works by sending input through the training sets and awards closest weight vector in each iteration. So if our closest vector, for example, in our new set is the 85 with 110 sales, if another one came in that's at 36 degrees and only 4 sales, it's going to reward our highest winner, the 110 sales, and say, hey, you're going to stay here. This other one we don't need. We're going to toss it, and we're going to give 1 point to this. And because it gave a point to 85 degrees with 110 sales, that vector is not going to get removed as easily. Unlike the 32 degrees with 0 sales, since it was never given a point, that's one of the first ones that will be removed. So as it's given more points and as it actually finalizes and improved data, it's going to keep throwing out older vectors that have less points. And the ones that get rewarded more points are the ones that it will keep. This is especially useful for forecasting, as you can give it a wide training set at the beginning, tell it what you want for a goal, and watch as it starts selectively choosing the data and output that you desire. From here, it allows our weights to be trained off a set number of training sets. So in this case, for example, we only want our Fahrenheit degrees from 32 to 110, but we also only want, we're going to say 60 records per space. So if it goes from 32 to different temperatures up to 100 and starts tossing out the ones with no points on them, you're going to find that eventually we should hopefully see 60 sale record days, anywhere between 70 to 90 degrees, showing maximum number of sales that would actually be obtained.
So it is now.
Sorry, Damian?
So yeah, I was with this entire time. So as you might have gathered, much of the mechanics of ML and AL is inspired by real-life neuroscience. That is, research in how our brains and human cognition actually work. So concepts originally from the field or starting points of virtually everything we have discussed today. So supervised learning methods, especially KNN, is inspired by Donald Ebb's principle, as we discussed, Abelian learning. And actually, I'd say that the beginning of ML was in constructing artificial brains. So this was huge in the 2000s and late 1990s. The realization that our brains are really just connected neuronal networks, and therefore we can model it computationally. So some important realizations: these neurons need energy and the networks need space. So our brain contains roughly 100 billion nerve cells, less, more like 90, but 3.2 million kilometers of wires, a million billion connections, all packed into a volume of 1.5 liters, only weighing 1.5 kilograms and consuming a mere 10 watts. So therefore, there's something about our brain that means that despite all of those literal billions of connections, there's something about it that means it only consumes a little bit of energy. Therefore, it's not so implausible that we could build such a brain using silicon chips and that it could consume, like, even if it consumed many orders of magnitude more, like 10 megawatts, that still wouldn't be completely infeasible if you get enough research funding. However, the main issue would be that heat produced by such a silicon brain would cause it to melt. So then the challenge here is to discover how the brain would operate so efficiently and economically and use similar principles to build brain-like machines. So this is partly where the concept of cost came from, in that the energy cost of signaling neuron-to-neuron communication is a major factor in how our brains operate. So around 50 to 80% of the total energy consumption of the brain is just consumed in the conduction of action potentials. Here, I guess it would be like analogous to back propagation and taking dot products along nerve fibers and in synaptic transmission. The rest is like overhead in manufacturing and maintenance. So then it's going to be, and it's true to the same extent in our neural network models. So, however, one thing to note is that compared to the speed of digital computers, the speed of nerve impulses is very slow, only a few meters per second, in contrast to our computers, which do things imperceptibly quickly. So, if we can model these parallel networks, then it seems like it won't be unachievable again. And so that's largely where the first neuronal networks came from the first digital brains. So a big solution, a significant proposal to solving this issue, which I believe was proposed by Hegel, was to reduce power and increase speed through adopting our by just turning back to how our brains function biologically. So we use analog rather than digital coding. In the building of artificial brains, this is known as neuromorphic engineering, in translating neurobiology into technology. So these systems code in continuous changes in voltages as opposed to zeros and ones. So these calculations can then be done in fewer steps because the basic physics of the silicon devices is exploited, and analog computation easily provides the primitives of a simple logical calculus: addition, subtraction, exponentials, and integration and derivation as a result. So then this structure would give rise to the neural networks we know today. So they would take learning rules that train the networks by modifying the strengths of the connections between the neurons, which is exactly how our brain works. Our brains grow and adapt through neuroplasticity and synaptic pruning, a little bit like use it or lose it. The part of your brain that you use the most, for example, the parts that are responsible for motor control, the synaptic connections are going to be strongest in an athlete, but say someone who's less athletic and isn't a world-class athlete will maybe have weaker synaptic connections in their motor cortices. And this is actually a lot like, this draws the analogy to how brains develop. So a 2-year-old brain actually has many, many, many more synaptic connections than an adult brain. But the thing is that they're a lot weaker. So then the thing is that by exposing it to external stimuli, i.e. exposing our code to training data, we let it determine what connections does it weaken as to reduce energy and what connections does it strengthen. And so with that, just as a baby become like a barely sentient baby becomes an intelligent adult, or a little neural network becomes one that can maybe even classify things more accurately than a human. So sorry for that somewhat long-winded tangent. Oh, sorry, another thing. So actually, sorry, no, never mind. It was covered in detail. So forgive the tangent. But with that, why don't we move on?
All right. So there's a few additional topics that we didn't feel the needed heavy slides for, but something that we could nonetheless go over anyways. One of the additional topics that we were considering is natural language processing, or NLP, which is the variable length processing of recurrent neural networks to make them ideal for analyzing handwriting and speech, the field of AI called natural language processing. Attached to these, which we should actually have this up so anyone can view through these slides if they wish, we are missing, unfortunately, a few slides, mostly around the neural networks that had some better examples of what the neural networks actually were. But for the most part, on the additional topics are links, which you'll be able to continue learning more about, as we were uncertain if we would have the time or the ability to go further into depth with these. For medical applications when it comes to AI, we have the myriad applications in diagnosis, electrical signal analysis, medical image analysis, radiology, and dendrograms. Dendrograms, especially in AI and ML, for what I've actually done personally through projects working with a couple of companies, especially with actually surprisingly microcatheter companies, has actually done AI to link different types of cells that are similar and put them together. When it comes with a dendrogram, if you have multiple different types of cancers, maybe brain cancer, skin cancer, lung cancer, continuing on and forth, what it does is it goes through and it takes the genomes of each cell in the body or each cell in the tissue given and says, all right, this genome for recurrent sickness is the same as this other genome that happened to be lung cancer. And it's different from all the other genomes, so therefore, this specific particle has to be lung cancer. And it continues grouping them in that similar way until it forms a giant graph of different types of cancers set up. That's actually been very useful in AI, especially when it comes to discovering a genome. AI has actually also been useful in our current issue with COVID-19. COVID-19, another small project I was working on or working with, depending on how you wish to call for it, is that it was actually going down the genome for helping analyze and showing the possible mutations that happen with it. This is where my part came in, where it was minor forecasting and predictive algorithms for the mutations that can happen. As we've unfortunately heard, some new strains have broken out in other countries, and this is not surprisingly new to the medical field. It's nothing that they weren't expecting whatsoever. AI and ML had actually shown that these were possible mutations of the strains and that it can mutate in other ways. As they create new vaccines for us and new come out, the vaccines isn't just for one strain, but if created correctly, should cover multiple strains and all possible mutations. This is where AI and ML hopefully come in to help solve our current COVID-19 crisis. A few other ones is other unsupervised algorithms are recommended lengths continuing on for a bit more learning, as our method of movements for estimated population parameters for expected values of powers of the considered random value. There's a little bit more about, we'll actually go through that in Wikipedia, and our principal component analysis, which is used in exploratory data analysis. Best fitting line minimizes average squared residuals with an orthonormal basis. Think of the x, y, and z axes and then change bases as needed. Our modern ML developments as well is that it's currently used in to recognize patterns and identify threatening activity for cybersecurity. This can be noted, especially for people interested in cybersecurity, that it looks for similar patterns and attacks in malware. Most malware these days can only enter through certain ports or certain bases, especially whether it's a program that's running or attempting to enter a port on a computer. By recognizing how these actually run, a basic AI can say, all right, using a predictive algorithm, we could say we have to watch these holes in the computer. and if they're attacked, then that's where it's most likely going to happen. And as new attacks happen in areas it's not expecting, it takes the training data and says, all right, this happens over here, or maybe this might happen. We also have more advanced autopiloting systems. This goes into our automotive, which is automated, so automated automotive vehicles led by Tesla as of currently. And as we talked about, especially with the reinforced learning, we want to actually make sure that it has multiple goals. It's continuing on because the task is to get somewhere, but we want to give it more than one goal because you can tell it get there as quick as possible, get safely as possible. But what if you want a combination? What if we want it to get quickly but safely? So we have to keep training and learning how to utilize the machine learning developments so that way in a reinforced learning situation, we can give it more than one goal and ask it to try to get more points if possible. Though one of the current issues that are popping up rather rapidly today throughout the field is the ethics and the future of AI, especially in advancing a field of safety, but also in the economy altogether. There are many people that are worried that robotics will replace the future, and it's highly unlikely it will. While AI is sophisticated and has come far, it still has very far to go, and AI is still far from perfect. It's made plenty of mistakes. Some of the actual manufacturing industries I've personally worked in, I've attempted to utilize with artificial intelligence or some type of machine learning. One, for example, is a plumbing factory called Plumpack. While working under Plumpack as a software engineer for a small term basis, one of the things I'd considered was how come they had people manually inspecting parts? There were people still on the line manually inspecting parts as they were made. Why can't a computer just simply take a look at it? As it would turn out, AI is actually not advanced enough to recognize small errors in a part that could make it weak. So if you have, for example, a J limb, which is a long, pretty much J-looking limb that's used in toilets, if there's a small dent in one of the bottom areas, it could be that it wasn't correctly filled in with either the correct metal or plastics. Therefore, if you put too much water pressure, if it bursts, it will be bursting from that point. AI, unfortunately, isn't advanced enough to actually recognize those minor issues. Or a human brain and a human eye recognizes those small problems and realizes, all right, this part is actually not able to be sold. So there's still more in concerning ethics, also when it comes towards the future, how it's applied to people, and how it can actually affect us all. For the most part, that is the overall show and our overall workshop on advanced AI. We hope you're able to learn quite a bit, and we thank you for joining us. If there's any questions, do feel free to ask at this time. We have a solid 15-20 minutes for any questions that wish to be asked.
All right. Before you guys get into any questions, can we have a round of applause for all the speakers today? They did a really nice job with the workshop, and yeah.
Yeah, thank you, Luke and Damian. That was really good. Okay. You can
Thank
snap if you'd like. The answer to a plethora of questions that I had coming into this. So thank you so much for that. You might want to cut the recording
Sure.
before questions in case people have any.
Give me a second here. Yeah, just move out that window here so I can tell it stop. And we'll